Today we're going to learn how to use the average atomic mass of an element with exactly two isotopes to work backwards and find the abundances of those two isotopes. This does require a little bit of algebra. Your first step is to identify what's given to you in the problem. You're going to be given the mass of the first isotope, the mass of the second isotope, and the average atomic mass of the element. And once again, this technique will only work if you know the element only has exactly two isotopes. Step 2 is to write out the general equation for average atomic mass. In this case, we know that if we take the abundance of isotope A and multiply it by the mass of the isotope A, and then we add the abundance of B times the mass of B, we'll get the average atomic mass. Now, this is going to be a little bit of a problem. Since this equation has 5 variables above, we are going to need to know 4 of them in order to calculate the unknown one. I'll show you a trick for that in just a second. Let's go ahead and plug in the data we were given. So let's say there is our equation, and I've highlighted things based on color. Let's say the mass of the first isotope is 52.22, the second isotope is 63.33, and the average is 56.78. So we can just plug those in right away and have our equation for this situation. But you're going to notice we still have 2 unknowns. We can't solve this if there are 2 unknowns. We have to know 4 out of the 5 variables in order to solve for the 5th one. So we're going to do a little trick. We know that since there are exactly 2 isotopes, we know that their relative abundances, those decimals, have to add up to 1. This is the same as saying for 2 isotopes that are percent abundances, they would add up to 100%. But remember, we need to use decimals called relative abundances instead of percent abundances for these types of equations. So if we put this algebraically, this means abundance A plus abundance B equals 1. And I can solve this, rearrange a little bit, and find that abundance B equals 1 minus abundance A. Let's use this fact. We're going to substitute. That issue we have with our 2 unknowns won't be a problem for very long, because instead of abundance B, I'm going to plug in what I just figured out. Abundance B is actually the same as 1 minus abundance A. So let's swap it out. We're going to substitute 1 minus abundance A instead of abundance B. And that leaves us with this equation. Now we only have 1 unknown, and we'll be able to solve for abundance A. But we are going to have to clean it up first algebraically. We're going to need to distribute and then regroup, simplify, and that's going to take a lot of algebra. So distribute, rearrange, regroup. I'm going to go through this quickly. You're welcome to pause and figure out what is going on after each step. There was our equation that we need to solve for abundance A. We see it appears 2 times. I'm going to distribute the 63.33 to the 1 and the minus abundance A. I'm going to move the abundance A times 63.33 to the right-hand side of the equation. Now, I'm going to subtract the left-hand abundance A times 52.22 because I see that this one was bigger, 63.33 versus 52.22. By doing this, I'll be able to group together these 2 terms since they have the same variable in common, abundance A. When I do that, 63.33 minus 52.22, I can clean it up just a little bit, and I get abundance A times 1.11. Now we're almost done. I'm going to take care of these terms by subtracting 56.78 from both sides, and I get 6.55 equals abundance A times 11.11. and we've reached our final step of division, and I find that abundance A is 0.590. That was a lot. This number should be between 0 and 1. If it's greater than 1, you've done something wrong. Step 7, really easy. We know abundance A plus abundance B has to add up to 1. So 1 minus abundance A gives us our abundance B. If A is 0.590, then B must be 0.410. Let's always check our work. We'll check our work by quickly calculating the average mass, but this time using the abundances we just figured out. Remember, average mass is just abundance times mass for one isotope, plus the abundance times mass for the other isotope, and that gives us our average. If we plug in the numbers we just figured out, 0.590 and 0.410, and we multiply them by their corresponding masses, we get 56.78 AMUs, which was the average atomic mass given in the problem. So if this doesn't match, you have made a mistake. Perfect timing.